Today we're going to be considering this problem from a Stanford High School mathematics competition that reads as follows. Determine m so that the roots of the following equation has 4 real roots in arithmetic progression. Before you start, there are 2 different paths for this, one that is more computationally heavy and one that is less. We're going to go over the proof that is less, but I'll give you hints for how to do the one that is more computationally involved. So try it for yourself and then come back for hints, and then we'll get on with the proof. Alright, for the one that is more computationally heavy, we're going to make the substitution u equals x squared, and then try to work with a normal arithmetic sequence, or arithmetic progression, to solve for these roots. You're going to have nested square roots, so you're going to need to find clever ways to simplify those, and to make it so you don't have to expand everything every time you want to solve an equation. But if you do that, you should get the right answer. Alternatively, for the easier proof, try to do some observations about arithmetic progressions and write it in an unusual way, and then consider the fact that there are four real roots for this function. Alright, so for this one, we're going to note that if you have, since you have 4 real roots, and our equation is symmetric in some sense, we'll see that you're going to have 2 negative roots and 2 positive roots. If we list them in, these outer 2 are the greatest magnitude ones, then we see that the inner ones are going to be the least magnitude, and we're going to try to find some relation between them. In particular, if we call this one A, then we see that this one is going to have magnitude minus A, since if you plug in A, minus A is the same thing when you put raised to the 4th power or square it. Therefore, this will also work. But then we'll note that we have an arithmetic progression so that there's a 2a difference between them. So that tells us the size of these outer 2. With that, we now have all of the factors of this, and we should factorize this entire polynomial in terms of these roots. And the first thing we note is if we have a minus a term and an a term, we have an x plus a and an x minus a term. So we use the difference of squares to write this like this. And the same thing is true for the 3a term. So we have an x squared minus 9a squared term. Now that we've introduced a, we can solve for m by FOILing this out and matching coefficients. In particular, we get an x to the 4th term out front. We get a minus, and then let's give a 1 plus 9, which we'll call 10, a squared x squared term, and then plus, of course, the 9a to the 4th term. And this gives us a set of equations by considering the coefficients, because we said that this should be the same as our original equation. Therefore, we get this pair of equations, 9a to the 4th equals m squared, and 10a squared equals 3m plus 2. In particular, we'll note that if we take we have some options, but what's the easiest way to do this? If we take a square root, we get that m is equal to plus or minus 3a squared. So we can substitute that in down here. Doing that, we'll get 2 solutions for m. One of them is integer and is of the form. It is simply just the number 6. And the other one is slightly more complicated and is negative 6 over 19. So we get m is equal to 6 or negative 6 over 19. To see this a little more clearly, how you get this is once you have these equations, you can rewrite it by squaring the second equation to write it in terms of the first equation, and you get 19 m squared minus 108 m minus 36 equals 0. And then you can simply apply the quadratic formula to get the roots here. Or you can factor this as m minus 6 and m plus 6 over 19. I'm sorry, 19m plus 6. With that, we have generated our two solutions, so we're done. Thank you for watching.